Welcome to section 7.1. Today we're going to learn about rational functions and simplifying rational expressions. So first we need to learn what is the definition of rational. Well, a rational number is any number that can be written as a fraction. So for example, 5/7 would be a fraction, right? So that's a rational number. The number 2 is also a rational number because it can be written as 2 over 1. So whole numbers are rational numbers. It could also be negative. It could have -2. Most decimal numbers can be written as fractions. For example, 1.5 is a rational number because it can be written as 3/2. The only numbers that are not rational are numbers whose decimals do not repeat. So for example, pi. Pi is the number that's approximately 3.14159, and then it goes on forever. And you might remember about pi, one of the things is the decimals never repeat. And if the decimals never repeat, that means there's no way to write it as a fraction or as a ratio of two numbers. So that's not a rational number. So what we're dealing with in this section is not really rational numbers, but rational expressions. So a rational expression is it's something that can be written as a quotient of two polynomials. So it looks like a fraction. So for example, remember a polynomial is something like a quadratic or a cubic or a line. It can have any x power though. So for example, let's do a cubic, x cubed minus x or minus 2x plus 3 divided by maybe say x minus 1. That's a rational expression because it's a polynomial divided by another polynomial. Basically, it's a fraction of two polynomials. A rational function, it's a function whose definition is a rational expression, so the only difference is it would say f of x equals . Okay, your domain. Again, that's the same thing. It's still the set of input values, or the x's, that can be plugged into the function. So just like in the previous section, when you're finding domain, the best way to do it is to find the x values not in the domain, and then your domain is everything else. Now because rational expressions deal with fractions, and you can't divide by 0, domain is usually an issue. So let's look at this one. What is the example, or what is the domain of this polynomial? And well, are there any x's that for any reason you cannot plug into any polynomial, really, something such as this? And the answer is no. There are no x values that you cannot plug in. No matter what number you take, you can always cube it, square it, multiply that by 2, subtract that from the cube, and add 8. So the domain of any polynomial is actually -infinity to infinity, or you might remember the abbreviation for all real numbers is that. Okay, but with, again, with rational expressions, we can't divide by 0. Now why not? You may be wondering, why can't we divide by 0? Well, there's lots of ways to explain it. A simple way is just to go back to what is the definition of division. So for example, if you have a group of objects, right, so here's a whole bunch of little objects, and say you want to divide this group into 2. Well, your answer would be how many are in each group of 2. So you could divide it and say there's one group, here's another, let's not count the dots, but let's say those are equal groups. Okay, so if you divide something by 2, you'd split it into 2 groups. If you divide something by 1, you're putting it into 1 group. So it would just be the whole group of dots. It would be however many are in that group, because when you divide by 1, it's how many are in this group of 1. Now if you divide by 0, you're trying to put it into 0 groups. Well, no matter what you do, you have dots and they have to go somewhere. You have these objects, right? You can't put them into 0 groups. The minimum number of groups you can put them in is in one group. There's no way to put them into 0 groups and make them all just disappear. So it just doesn't make sense. And there are other ways to think about dividing by 0, but that I think is a pretty simple explanation. So we can't ever divide by 0. Alright, so let's look at finding domain of some rational expressions. Alright, a rational expression is defined everywhere except for where its denominator is 0. So for example, x squared plus 3 all divided by x. Well, it's undefined. This whole expression is undefined if x is equal to 0, because if you put a 0 right here in the denominator, well, you can't divide by 0. So it's undefined where that denominator is 0. Therefore, its domain is everything except 0. So it's the set of all x such that x does not equal 0. Now here's a slightly different example. Let's find the domain of this rational function f of x equals x squared plus 1 over x minus 6. Now this is different because you have to think a little harder and ask yourself, what is the x value such that if you plug it in, you'll get a 0 in the denominator? Now the answer is not 0. Okay, it's not 0 because f of 0, let's take f of 0. F of 0 would be 0 squared plus 1 divided by 0 minus 6, which is 1 over negative 6. We're dividing by negative 6 when we plug in 0 for x, not 0. So here you probably can see it. Okay, you go, okay, if you plug in 6 for x, we'll have 6 squared plus 1 over 6 minus 6, and then we get a 0 in the denominator, which we can't do. So therefore 6 is not in the domain. So the domain is everything except 6. So the domain would be the set of all x such that x does not equal 6. Okay, now a more systematic way of going about it that will help us on these more difficult problems, such as the next one, is to instead set the denominator equal to 0. So you take that whole denominator, x minus 6, we set it equal to 0, and we solve. And we get x equals 6. So that's the thing that's not in the domain. So you can also just set the denominator equal to 0 and then solve for x, if you can't just guess it by looking at it like we did in this case. Okay, let's do a slightly more difficult example here. Let's find the domain of f of x equals 5x plus 4 over x squared minus 3x minus 10. Now this one's definitely too hard to do by guessing and checking because we have a whole quadratic in the denominator, and there's probably going to be, well, there may be 2 answers actually, because quadratics, when you set them equal to 0 and solve, as you've seen, you get 2 answers often. So instead I'm going to use this method of setting the whole denominator equal to 0 and then solving. So let's see, hopefully this factors, and 10 factors into 5 and 2. I think I can get a 3 here from 5 and 2. So how about 5, 2? One of them must be positive and one must be negative so that they multiply to negative 10. And I want them to add to negative 3, so I'll put the negative in front of the larger number, 5, and the positive in front of the 2. Remember, then we set each factor equal to 0. So we have x minus 5 equals 0. Solving that for x gives us x equals 5. And then we set x plus 2 equal to 0. Solving that gives us x equals negative 2. Now those are not the answers. In fact, that's the exact opposite of the answers, because those are the 2 values of x such that when you plug them in, you get a 0 in the denominator. So let's check that and make sure that we did do it correctly. So if I take f of 5, I'll get 5 times 5 plus 4 in the numerator, divided by 5 squared minus 3 times 5 minus 10, which is 25 plus 4 is 29, divided by 25 minus 15 minus 10 is 0. So that is true. When you plug in 5, you get 0 in the denominator. So that is not in the domain. And let's check f of negative 2. Okay, really, you might have noticed it doesn't even matter what you get in the numerator. All we really need to plug it into is the denominator. So remember those parentheses around the negative 2 before you square it. And again, then we get 4 plus 6 minus 10. 4 plus 6 minus 10 is 0, so that also does not work. So therefore the domain is everything except negative 2 and 5. Let's write it 2 ways. because there's two fairly simple ways to do it. You could say the set of all x such that x does not equal -2 or 5. Or in interval notation, you could say from -infinity up to, now the first of these numbers that you hit is -2. Now we don't want to include -2, so we exclude it with the parenthesis. We start right after -2, such as at -2.00000000001, and go all the way to 5, but we don't include 5, so another parenthesis there. And then we pick up right after 5 and go on to infinity. So there it is in interval notation. Here it is in set builder notation. Okay, next one. Find the domain of x squared minus 9 all divided by 4. Now there's no x's in the denominator. So no matter what x you plug in, 4 will always be the denominator. So no matter what you do, there's no way to get a 0 in the denominator. So therefore the domain is all real numbers, or from -infinity to infinity. Okay, so that's how you find domain of rational functions. You set that denominator, you take this whole denominator, and you set it equal to 0. That's the important part, and then you solve. Now on this one, if we had done that, we would have gotten 4 equals 0. And obviously that is not true, so you would just say no solution. That's how you would write that up. Alright, next we're going to look at simplifying rational expressions. How do you simplify them, not just how do you find the domain. First, let's look at how do you simplify a regular fraction, because it follows a very similar pattern here. So this is a bit of review. Remember, a fraction is in lowest terms or simplest form if the numerator and denominator have no common factors other than 1 or -1. Okay, so to simplify 27 over 18, I'm going to write this out in a very specific way, okay, because the point here is not to get the answer. The point here is to look at why do we break it down the way we do, so that you'll understand when we do it with x's. So what I'm going to do is break down 27 and 18 into factors. Okay, now 27, we don't have to break it down into prime factors, or we may or may not, we don't know. 27 can break down into 9 and 3, and 18 breaks down into 6 and 3. And so what we can do is we can say, well, this is the same as 9 divided by 6 times 3 divided by 3. You should have already learned this, but we'll do this again with rational expressions soon. And that is when you multiply two fractions, you actually multiply the numerators together and the denominators together. So I'm unsimplifying this already simplified fraction. Oops, that should say a 3 there. Now 3 over 3, 3 divided by 3 is 1. So here we really have 9 divided by 6 times 1, which is 9 divided by 6. Now can we go any further? Okay, well, let's see. Actually, I'm going to cross those out. That's the common way to denote 3 over 3. So you say, do 9 and 6 have any more common factors? Well, yes, they do. They have a common factor of 3. 9 we can still break down even further into 3 times 3. 6 we can break down into 3 times 2. Now, normally you don't actually split it into two fractions before canceling, but the point is that you can. Okay, so I'm not going to split it into two fractions, because everything is being multiplied. So I know I could split it into two fractions and I would get the same thing I did here. I get 3 over 3, which is 1. Instead, I'm just going to do it like that and cancel those factors right here without rewriting it. And now 3 and 2 have no common factors, so that's fully simplified right there. Okay, now the key is common. They must have common factors. Common factors being the key word here. Now let's do the same thing and try to simplify a rational expression. So first example, does 3x divided by x simplify? Well, let's see, can we break it up the way we did up here? 3x divided by x. And the answer is yes, you could break this up into 3 over 1 times x over x. Well, x over x is equal to 1, those cancel. So you just get 3 over 1, or 3. So yes, that one does simplify. Next question, does 3 plus x all divided by x simplify? Now here's the kicker. Can you split this into a product of two fractions? Okay, does this equal 3 over 1 times x over x? The answer is no, because you're adding these two fractions. Okay, if you wanted to unadd, you would say that's 3 over x plus x over x. Okay, you could do that because when you add fractions, remember you add the numerators, which we've done, but the denominators stay the same. Now if you do that, sure, x over x is 1. Now it doesn't just go away. X over x equals 1. So this is 3 over x plus 1, but it is not the same as 3 over x. So this actually does not simplify. This is its simplest form. This is another equivalent form over here, but this does not simplify. The main reason here is because we're adding in the numerator, and the same is true as if you were adding in the denominator. If you're adding or subtracting two terms, this is not factored. Now something has to be completely factored before you can cancel like this. Okay, put a big note here. Must be everything, numerator and denominator, must be completely factored before canceling. Now this is not, this one, first one up here is factored because we have 3 times x over x. Something is factored if all the pluses and minuses are inside parentheses and all of your factors are really being multiplied and divided in each the numerator and the denominator. This is not factored because we're adding, so it is definitely not factored. Okay, therefore nothing cancels. So that's the difference, is what I just stated right there. Alright, let's do another example. Let's simplify x plus 4 all squared divided by x squared minus 16. Now the first thing you might want to do here is you see x plus 4 quantity squared, your instinct is to expand. Okay, that's actually not going to help us. I'm going to show you why. If you expand, remember that's x plus 4 times x plus 4. So you actually have to remember to FOIL up there in the numerator. And there's nothing to expand in the denominator. Now if we FOIL up here, we have x squared plus 4x, so plus 8x, plus 16, divided by x squared minus 16. Can you cancel factors? No, because we're adding terms in the numerator and subtracting in the denominators. So you cannot cancel because it's not factored. So although your instinct may be to expand when you see something like this, you actually want to factor everything when you're simplifying rational expressions. The goal should be to factor as much as possible. That way you can then cancel common factors. So instead, let's see if we can factor this. Now the numerator is already factored technically. It says x plus 4 times x plus 4. That's factored because the plus and the plus are inside parentheses. The big thing here is we are multiplying two factors. We're multiplying two things. So it is factored. And the denominator, does x squared minus 16 factor? Hopefully that rings a bell. 16 is a perfect square. So you have a difference of two squares, x squared minus 4 squared. So that, by that difference of squares rules we learned in chapter 6, factors into x plus 4 times x minus 4. Now it's fully factored because everything in the numerator is being multiplied and everything in the denominator is being multiplied. The pluses and minuses are inside of factors, so they're okay. So what you can do is you can cancel whole factors that are the same. In this case we have an x plus 4 in the numerator and an x plus 4 in the denominator. So those actually do factor. And then we're left with an x plus 4 in the numerator and an x minus 4 in the denominator. So there is that expression simplified because it had common factors in the numerator and the denominator, so we took those out. So we must factor first. Okay, let's try another one. Make sure you're trying these on your own first. So in the numerator, there's nothing we can do to simplify or rewrite it really. It's just 3y cubed. In the denominator, it's not factored because we have that minus right there, so we need to try to factor. And we have a 4th degree polynomial in the denominator, because of that power of 4 there. So this is not a quadratic, it's not going to be anything fancy. So let's just see if there's anything we can take out of both terms. And yes, there is. We can take at least a 3 out. 6 and 3 have a common factor of 3. And they both have 3 y's. We have 4 y's in the first term and 3 y's in the second term. So I'm going to take out 3. Then I'm left with 2 times y in my first term minus, now I actually took the whole second term out, 3y cubed. I factored everything out, so I'm left with a 1. Okay, and now we look for common factors because it is factored. Everything in the numerator is multiplied, and so is everything in the denominator. And actually, not only do the 3's cancel, so do the y cubed. Y cubed divided by y cubed. And remember, when everything cancels, you're really left with a 1 because that's the same as times 1 up there in the numerator. So you have 1 over 2y minus 1. So there it is in factored form. And let's give this next one a try. Now this one we have 3 terms and it is a quadratic. So we're going to use the quadratic factoring methods in both the numerator and the denominator. So let's hope this factors. Now if it doesn't factor, then this thing just won't simplify. Okay, now in the numerator, the easy part here I see is the 1 for the last term, which means both of those must be a 1. The first term must be 5x squared. The only way to break down 5 is to 5 and 1, so let's go with 5x and 1x. And then the numbers must multiply to a positive number, but add to a negative number, so they have to both be negative. Okay, let's check over here to the side. I'm going to FOIL this out. 5x times x is 5x squared. My outside terms are 5x times negative 1, that's negative 5x. Inside terms, negative 1 times x is negative x. And the last terms are negative 1 times negative 1 or positive 1. And let's see, that does simplify. Negative 5x minus x is negative 6x. So that is correct on the factoring there. Then in the denominator, our first term is 3x squared, so we're going to have to break that down into 3x and 1x. Then the last term is 7. Now the only way to get 7 is to do a 7 and 1. The question is, do you put the 7 here or do you put the 7 here? Now if we put the 7 here, let me just do it for a moment. If we were to put the 7 there, we would multiply for our outside terms 3x times 7, which would give me 21x, which is so much bigger than 4x that I don't think that's correct. So I'm going to go put the 7 here and the 1 there. Now they need to multiply to this negative number, yet add to a positive number. So we want to put the negative in front of what's going to be the bigger term. Now this outside term will multiply to 3x times 1, or 3x. The inside terms will multiply to 7x. So I'm going to put the positive in front of the 7 so that it will add to 4x. And if you check, this does work. 3x times x is 3x squared. My outside terms are negative 3x. Inside terms, positive 7x. And the last terms are negative 7. Negative 3x plus 7x is 4x, so that does work. Now let's take a closer look at it. Do we have any common factors? Yes, we do. We have x minus 1 and x minus 1, so those do cancel. And so we get 5x minus 1 divided by 3x plus 7. So there is the same expression except it's simplified. Alright, these next two are a little interesting. So in the first one, it's not factored. We have 5 plus x. And in the denominator, we have x plus 5. Also not factored, and neither of those is going to factor. However, if you think of it as this, 5 plus x divided by x plus 5, maybe you just add parentheses around the outside, it doesn't hurt. You can see that these are actually the same factor because order of addition doesn't matter. X plus 5 is the exact same as 5 plus x. Okay, so I could reorder the terms in that denominator and write that as 5 plus x. Why not? Just switch them around and then they cancel. So you're simply left with 1. Okay, the next one is very, very similar but a little different because we have minuses. We we have 5 minus x over x minus 5. Now 3 minus 2 is not the same as 2 minus 3. So these are actually not the same. But what we can do, you may remember this from before, is we could factor out a negative 1 from one of the two terms. So I'm going to factor out a negative 1 from the numerator, in which case I'd be left with negative 5 plus x, and in the denominator I have x minus 5. Now if it helps you, add some parentheses around that, because you can see it's very similar to this factor in the top, negative 5 plus x. We can reverse those two terms. And if we reverse those two terms, we get the negative of x minus 5 over x minus 5. And now they look the same, x minus 5, x minus 5. So we're left with negative 1 divided by 1, or just simply negative 1. Okay, and make sure you're trying these on your own each time. Let's try another one. So simplifying this, okay, so we have a quadratic in the numerator, but it only has 2 terms, and a quadratic in the denominator, which has 3 terms. So remember, when you factor quadratics that only have 2 terms, there's no need to set up the sets of parentheses like this, because that only works for things like here in the denominator, quadratics with 3 terms. But in the numerator, let's see, it looks like we can take out a 3 out of both terms. So we're left with 1 minus x squared. And in the denominator, x squared breaks down into x and x. Negative 2 breaks down into 2 and 1. And we want them to add to positive x, so I'll put the positive with the 2 and the minus with the 1. And you can double check that will FOIL out correctly. Well, if you take a look at it, it is factored because we have 3 times this whole factor in the numerator. Every plus and minus is inside a set of parentheses. However, none of the factors are the same, so at this point it's looking like it doesn't simplify, but before we jump to that conclusion, we need to try a little harder to factor more. Okay, now the denominator, x plus 2, that's not going to factor anymore, and neither is x minus 1. But in the numerator, we have 1 minus x squared. Now that's a difference of 2 squares. That can be thought of as 1 squared minus x squared. So that factors by that difference of squares rule into 1 minus x times 1 plus x. And the denominator stays the same. And remember, be sure you're rewriting the whole expression each time to keep your work simple and clear. Okay, and we look at it a little closer, and we have 2 terms that are close but not quite the same. We have 1 minus x and x minus 1. So we're going to use the same trick we did in this previous problem up here. If the minuses, or if the terms are reversed but being subtracted, so 1 minus x, x minus 1, the trick is to factor out that negative 1. So factoring out a negative 1 I'll do it from the numerator. Let's go down here, gives us negative 3 times negative 1 plus x times 1 plus x, all over x plus 2 times x minus 1. And at this point, you can probably tell that they're the same. Negative 1 plus x is the exact same as x minus 1. You don't actually have to rewrite it like we did up here. You can, at this point, just cancel those. So we're left with negative 3 times 1 plus x over x plus 2. So you can either leave your answer like that because it said simplify, it did not say factor, although factoring is a part of simplifying. Or if you felt like it, you could redistribute that negative 3 in the numerator to get negative 3 minus x, minus 3x over x plus 2. Now I typically tend to stop at the earliest possible step because if you keep going past what you need to do, 2 things. 1, you're wasting time, and 2, you could possibly make a mistake whereas you already had the right answer. So I can't tell you how many times I've seen students get the right answer and then keep going and mess up. So just stop when you have it correct is my recommendation. Okay, let's try a couple more. Make sure you try these first on your own. Let's simplify x cubed plus 27 all divided by x plus 3. Now at the first glance you say, well, it's not factored, and x cubed and 27 have no common factors, so that's not going to factor. And x plus 3 is as simple as it gets. But actually, x cubed plus 27 does factor. That is a sum of 2 cubes. Because we can think of x cubed plus 27 as x cubed plus 3 cubed. And remember, there's a special factoring formula for a sum of 2 cubes. I'm going to flip back on my notes here and find that real quickly. Okay, it's here in section 6.5. And right here we have factoring the sum or difference of 2 cubes. A cubed plus b cubed factors into a plus b times a squared minus ab plus b squared. Remember, make sure you do memorize both of these as I asked you to, so that you don't have to go look it up every time. So a cubed plus b cubed factors into a plus b times a squared minus ab plus b squared. So let's go back to where we were and write that in first, and then we'll apply it. Okay, a cubed plus b cubed factors into a plus b times a squared minus ab plus b squared. Therefore, applying that to this, so now I'm going to factor it, actually I want to factor it up here in the problem. Applying that to this, we actually have in the numerator, let's see, a is x, b is 3 here, so we have x plus 3 for a plus b times a squared, so x squared, minus ab, so minus x times 3, I'll write that as 3x, plus b squared, so plus 3 squared, which is 9. And luckily we have two common factors, x plus 3 and x plus 3. And so what we're left with in the denominator is 1, so we can just write this as x squared minus 3x plus 9. So there it is, fully simplified. And let's try one last one. In the numerator we have a quadratic with 2 terms. So let's see, we can take a 3 out of it. We're left with x squared plus 2. And in the denominator we have 4 terms, and it's a cubic. Now there's only one strategy that we've even learned to factor a polynomial with 4 terms, and that is factoring by grouping. So let's see, let's try grouping the first 2 terms together and the second 2 terms together and see if that works. So I'm going to try grouping this as x cubed minus 3x squared plus 2x minus 6. So the numerator we'll just rewrite. And the denominator, let's see, so we're looking for things we can factor out of each term. In this first group, I can take out an x squared. So I'll take an x squared out of that, and then would be left with x minus 3. Then we have a plus. Okay, is there anything I can take out of 2x minus 6? Well, we could take out a 2, so we'd be left with 2 times x minus 3. And yes, factoring by grouping did work because we are left with 2 common factors, x minus 3 and x minus 3, which we can now factor out of the whole denominator. So again, I'm recopying that numerator. Oops. So we have, if we factor out that x minus 3 from both of those terms in the denominator, then in the first term I'm left with this here in pink, that x squared, and in the second term I'm just left with that 2 in pink there, so plus 2. Alright, now it's fully factored. It was not fully factored at this step right here because we still had this plus, which was not inside a set of parentheses. So we're adding 2 terms here in the denominator, but now we're multiplying 2 terms with big times. So it is fully factored now, and luckily we have 2 of the same factors, x squared plus 2 over itself. So we're left with 3 over x minus 3. Well, that one simplified a whole lot from its original form. Okay, so there's plenty of examples there of simplifying rational expressions. Mainly you factor first and then cancel terms. But make sure you don't do this mistake and try to do like this. This is probably my worst pet peeve in all of math. Right here is when I see, oops, that's just x. Is when I see this. people canceling those x's. Those don't cancel. It's not factored. Okay, that does not equal 3. All right, that is wrong right there, what I just wrote. 3 plus x divided by x is not factored, so you cannot cancel x's. Okay, if it's not fully factored, don't cancel. All right, let's look at a couple of different equivalent forms. This is because you and your neighbor might both have the right answer, and it might look different. So you're going to have to get used to that. It's going to happen more and more often. So let's look at some of the different correct forms of this expression. There's 4 other ways to write it, and they all have to do with moving negative signs around. Okay, one way is you could put this negative in the numerator. So you could have the negative of 3x plus 7 divided by x minus 6. Or you could distribute out that negative, and so you'd have negative 3x minus 7 over x minus 6. Those are the same. Or you could have, instead, I'm going to come back to the original form for this one, you could put that negative instead in front of the denominator. And write it as 3x plus 7 divided by the negative of x minus 6. Or you could distribute out that negative within the denominator. So you'd have negative x plus 6. So all 5 of these ways of writing it are completely equivalent. They're the same. Okay, what you don't want to do is this. This would be wrong. Is to say that the negative of 3x plus 7 all over x minus 6 is to equal to, now there's only one negative sign here. Okay, it means negative 1 times this whole fraction. All right, it does not mean negative 1 times the numerator and negative 1 times the denominator. That is not right, okay, because there's only one negative, negative 1 times the whole fraction. It's not negative 1 times the numerator and negative 1 times the denominator, because in this case, those negative 1s cancel, and we just changed the expression. Okay, so that's not right. So if you have a negative out front, it can go in front of either the numerator or the denominator, but not both. All right, and one last thing to notice here is that rational expressions and their simplified form are slightly different. They're the same everywhere except at values which make the denominator of the original expression 0, but not the simplified expression. Okay, so for example, this one here, x plus 4 quantity squared over x squared minus 16, we found simplifies to x plus 4 over x minus 4. So the original expression has 2 x values at which it doesn't exist. If x is 4 or if x is negative 4, you'll get a 0 there because negative 4 squared is 16 as well, minus 16. But the simplified expression is only undefined at x equals 4. So that one is only undefined at x equals 4. So the domain of the original expression and the domain of the simplified expression are not exactly the same. So it's something to be aware of, that when you simplify a rational expression, its domain may change. Okay, that's it for section 7.1. Tune in next time for 7.2.